Inscribed angles. Inscribed angles. This is where things start to get crazy. Okay. Arcs. We've been talking about how arcs are measured in degrees. We're talking about the measure of this arc as the amount of degrees it goes around the circle, and that's defined by the angle here at the center. You can also have other types of angles related to a circle. We're not just going to talk about the angles that are vertexed at the center. There's some other ones. Here's the first one, inscribed angle. Now, what's weird about this is this came up a lot already in the homework for 9.3 and 9.4. They're asking you to apply the rule you're about to learn now, this one, and some of those problems, and it's kind of strange. Anyway, that rule is about inscribed angles, where the vertex is on the circle, and when you have a vertex on the circle, and these two, the angle that's basically made by two chords, which may have nothing to do with the center of the circle, there's an arc that's going to be in the interior of that angle. That arc is referred to as the intercepted arc. Got a lot of words that start with I in this chapter. We got inscribed, we got intercepted. The intercepted arc is the one that's inside the interior. Okay, there's another word that starts with I. If it's in the interior, on the inside of the inscribed angle, it's called intercepted. Is that enough for you? All right, so there you go. This arc AC has a lot to do with angle B. In fact, what it has to do with angle B is that the measure of that angle down here at B is half of this angle in here at D. Now there's a long proof of that in the book. I tried to show it to you Friday in class, why this angle has to be half of this one, but really it's so unrelated, and it's so I don't know, I guess I'd call it cumbersome. It has to do with making this radius at BD here, and then you have these two little isosceles triangles, and you measure the angle that's exterior to those, and it has to equal the other two, and you know that it's isosceles, and if you add up half of this one and half of this one, it's going to be half of the total. Anyway, I can go over that more if you want. I'm not going to ask for the proof on the test. What is going to be on the test, a lot of, is problems where you know one of these and you got to find the other one. And the whole story is whatever this is half. Double and half. Okay? And it doesn't matter where this point B is on the circle. It could be anywhere. And you get the same, it will always be the same angle, which is kind of hard to believe. Here's that same graphic, but actually in Sketchpad. Let me move this down so you can see it better. And here's this measurement. Yeah, if I move, okay, that's overlapping, sorry. Yeah, I have this arc AC made here. So the measure of angle ADC is given by this measurement up here. I can make that, let's make it a nicer number, like 56 maybe. Then all these are going to be exactly half. And it doesn't matter where I have it. And I can actually move this, and notice how the thing doesn't change. Anywhere along here, notice all these angles are congruent. And that, at first, that's kind of wacky. Like, why should that be? If I move it inside here, of course, it's going to be different. Now it's 151 degrees, because look how big that angle is. It has some sort of relationship with this, which we'll talk about perhaps later. But, yeah, no matter where you are on this circle, if it intercepts a 56.31 degree arc, okay, it doesn't look like it's exactly half. It's because of the rounding. Let me get an even decimal. Yeah, if it's 58.2, then the angle at the other end of the circle, that should be exactly 29.1. You can see that for all these. This angle out here is half of this angle in here. Okay. Just thought of one other thing here I should show you while I'm at it. Notice how this angle, how I move it around, it's always the same. It's also going to be the same if I move it all the way up so it's actually on this point A. Now, it might disappear when I do this. Yeah, it's going to kind of flop around here. If it's right on it, it starts to look like, well, what does that start to look like when this is starting to get to the point where it's just touching at one point here? It turns out that if this is actually even a tangent, this will be the same measure as all these, which kind of makes sense here. If it's right there on it and it's actually tangent, that would be tangent. That would be perpendicular now to this radius at D. It has the same measurement as if it was just a little bit over here. So that's actually one of the last theorems we learned today. But I think if you're seeing it in Sketchpad like this, how this angle is always the same size, no matter how I move this around the circle. It's always half of this arc. It's also true at a tangent. Okay, that brings us to our first video question. Why should it be that any angle that intercepts the same arc be congruent? In other words, back to this, why should all these angles be the same, like all these little ones I have here? Why is it that all these have to be the same size? Well, this kind of has to do with that proof I said I wasn't going to show you. Let's just talk about, let's hide all these because this is kind of in the way here. Get rid of these just for now. I'll leave the points there because I think I will bring those back later. But this this angle, why should it be the same no matter where I move it? Well, think about this. Think if we had all these radii drawn in here. Can you see those? Oh, that one was already there. Right, but let's, oops, didn't want to do that. If I draw the three radiuses of that circle in here, so if it's this one and this one and this one, I'll change those to red so you can tell what I'm talking about. Oh, and I'll make them all thick, why not? Or I'll make them all the same thickness. Those two are going to stay dashed because that's the arc we're talking about. Anyway, these two triangles, I'll do it here so you can kind of see them. If I do that, actually you can still see them, but they overlap worse. These two triangles, no matter what I do, these are isosceles triangles because they both have two sides that are made up of a radius of the circle. And the radius, all radii of the circle is the same. So DG equals DC, so that's an isosceles triangle. DA equals DG, so that's a really skinny little isosceles triangle. Then if you think about it, what we're asking here is why is this angle always the same? This angle at G, why is this always the same as we move this thing around? Well, think about what, this little angle here and this little angle here, they make up angle G when you add them together. I can make this a little wider so you can see better. This little angle here at G, the DGC angle, that, since it's an isosceles triangle, that's equal to this one up here. And this one down here, that's equal to this one up here. And those are both related to these bigger angles at D. Like this big angle inside D is 180 minus 2 of these, and this big angle at D is 180 minus 2 of these. And in a sense, if you think about that, as I move this solid red segment around the outside of this big reflex angle here, that sum isn't going to change. Like whatever this side equals plus whatever this side equals is staying the same. I'm just moving out the thing around in the middle of this. So as I do that, these guys ought to add up to be the same leftovers of 180 in each one of the triangles, which is why that stays the same. So it's because this is a radius of a circle. It's because these triangles are always going to say isosceles, which is because of the nature of the fact that they're radii of a circle, is going to ensure that the angles are in that relationship of basically a sort of extended it-bat kind of deal. And because this angle isn't moving, then the sum can't change. Since the sum can't change, then when I add up one of each side of each triangle, it's going to be the same every time. So sorry, that was kind of a long answer, but and again, I'm not going to ask you to do that on a proof or proof on a test. But I think it's good to know where that comes from because this is a really easy thing to forget because it's kind of surprising, really, that all those angles, because they kind of seem like they're moving around kind of randomly in that circle, that they would always have the same measure. Choose a case and decide and prove why is it that the inscribed angle is half. Again, not going to ask you to do this later, but for the video I think it's a good idea. Why is it then that this total here, why is that, oh it doesn't mark very big, is going to be equal to half of that? What happened to my little mark? Why is it going to be half of that? And that has to do with, I'll let you write this out, but it has to do with what I just said about the isosceles triangles. Like whatever, I don't want to do this in numbers, I want to do it in variables so you can see that it's going to be true all the time. This little angle here is kind of everything except this big one here. Whoa, what happened there? With 360, like it's 360 minus this whole thing. How come I can't draw on that little? I could draw it here. How come I can't draw inside there? Anyway, this big reflex angle minus, subtract from 360, that's what's left here. And that big reflex angle gets divided into two pieces for the big obtuse angles in the, the big obtuse angles in the isosceles triangles. And then what's left out here then in each isosceles triangle is equal. And so basically, let's say I have an angle that's x here. I have an idea. Just give me a second. Okay, I think I got it now. Let's say that this angle has a measure of x degrees. This one also has x degrees because that's an isosceles triangle. Let's say this one has y degrees. This one's also going to be y degrees. Then this whole thing, the angle in question here, the inscribed angle is x plus y that I'm trying to show. And I'm trying to show why is that equal to half of this thing. Let's call it z. Why is that equal to half of z? Well, think about extending this thing. Extend that line. And what is this over here? This angle over here is an exterior angle to this triangle DGC. And remember, in exterior triangles, or sorry, yeah, exterior angles and triangles always have this relationship. Angle 1 here equals angle 2 plus angle 3. We had this a long time ago. Measure of angle 1 equals, and this is the heart of all these proofs, measure of angle 2 plus the measure of angle 3. Well, in that case, here, this thing is going to equal x plus x. And then the thing over here is going to same thing. It's exterior to this triangle with the y's, and it's going to equal y plus y. So altogether, z really equals 2x plus 2y. And what's half of 2x plus 2y? I'll let you fill in that blank, but that's pretty easy to figure out why that does actually equal x plus y. So when I said choose a case, I was talking about try to pick one of the ways this can happen, because you should actually prove that 3 different ways if you're going to prove it. You should prove, well, what if the inscribed angle kind of includes the chord, and then your isosceles triangles look like that? Or what if, okay, here's my chord, my central angle for the chord, what if it's over here? That's a little bit different, because now my isosceles triangles aren't really arranged in the same order when I make the 3 isosceles triangles, or the 2 isosceles triangles. And what if it's right on it? Like, what if there's my central arc and my chord, and then here's my inscribed angle? Why is that half of that? And it looks a little bit different. So your job is to pick one of these 3 and then say, well, why is it? Okay, I'm going to move on to the next new thing here, which is why is it that if you have a semicircle, how come that's exactly 90 degrees? Can I get rid of my ink here? Yeah, good. If I made this be a semicircle, if I made the arc here AC be exactly 180 degrees, which is really hard to get perfect. See, look at that. Yeah, it's almost 180. Why will this be a right angle? Well, think about that. It's going to intercept this arc. If this arc is 180, this has to be half. So if this is exactly a diameter, this has to be exactly 90 degrees. And it looks like it's pretty close now because this is really close to 180. There's other ways to think about that. One is if you have a triangle, and now this is one line. No, normally on these arcs, like that's not really straight one line. But if it is one diameter, which it would be if we were actually talking about 180. Now I've got a situation where I have a triangle and I have this point here, D, that's equidistant from all these points here. We had a theorem earlier about right triangles, and if it's a right triangle, then the midpoint of the hypotenuse is also that same distance away from the right angle. The converse of that's also true. So that's what we have going on here. You've got a point equidistant from 3 corners on the side of a triangle, equidistant from all 3 vertices, then that triangle must be a right triangle. The thing is, you're going to start seeing that one a lot. The fact that if you've got a semicircle and you inscribe an angle in it, it's going to be a right angle. That comes up in all branches of math lots of times, in trig and in algebra 2 and stuff like that. So that's a good one to keep in mind. Okay, inscribed quadrilateral. So if you've got a circle and you've got a quadrilateral, if a quadrilateral can go in here, and not every quadrilateral can go in there. This is kind of a strange one. Kind of looks like an isosceles trapezoid, but it doesn't have to be. Then why is something like this? Why does that have to be supplementary to that? Well, and this is just one case. There's more than just this to it. But think about the arcs that thing cuts off. They both cut off arcs that end at point A and point B. This 1-tick arc here cuts off an arc that's that size, and this 2-tick arc here, that cuts off this arc here. The inscribed arcs here turn out to be sort of major arc AB and minor arc AB. Well, this one's half of the minor arc, this one's half of the major arc, and what should they add up to? The major arc plus the minor arc? Well, that ought to be 360. And half, so the total arcs of interception here on that sum of angles is 360, but remember, inscribed angles are half. So guess what? Those 2 angles have to be supplementary. And that's actually about it. The chord tangent theorem I talked about at the beginning when I was talking about the inscribed angle theorem. So someone asked if I could do something from the problems that were a little bit more like what you're going to be doing for homework. So here you go. Okay, number 7, we're supposed to find the measure of x and y and z. Z is this angle in here. And all we know about this is 76. Well, the 76 is an inscribed angle. This is the arc that it intercepts, so that's over here. So I know this arc over here, if I really cared about knowing that, would be 176 times 2, which is 152. So the rest of the circle over here, from sort of this point all the way around to there, has to be the rest of 360 with that. 360 minus, I've got 20 seconds left, 152 divided by 2, that would give me angle x. Sorry, 15 seconds. This piece over here and this piece will be the same. Y, 10 seconds. Y is going to be double of x, whatever that is, and I guess I'm going to have to show you that in class. Sorry, I tried.